Let's investigate a more complicated problem. Here we will use both kinematics and Newton's law to get to our answers. Alright, so let's see what we have here. We have two mass blocks and the system is connected via a massless cord or a massless string and stretched over a massless frictionless pulley. Alright, so there are some things to process here. It is said that the surface on which M1 is resting is smooth. This means the surface is frictionless. Alright, and the cord is massless, the pulley is massless and frictionless. This all means that on both sides of the pulley, the tension exerted by the strings or by the cord would be the same. It wouldn't have been true if either of these had masses or if the pulley had friction. Alright, now our first job is to find what the tension in the cord is. Alright, when the system is released from rest. First of all, we draw free body diagram, otherwise we cannot progress. So free body diagram for two of the boxes. For M1, what do we have? It's resting on a surface before it is released. So this is M1. It will have a weight, so M1G. M1 is 0.2 kilograms, so 0.2 times G is the weight. It will have a normal force, let's call it N1, which will be exerted by the surface on it because it is resting on it, and it has no friction because the surface is smooth, but it is attached to a rope, and the rope, as we know, or any ropes will pull a mass. So that pulling force is what we call tension. Let's call this T1. For M2, what do we have? M2 is hanging. It's hanging freely here. So M2 will feel a weight, of course, because it has a mass of 0.04 kilograms. So 0.04 times G. And then it will not feel any normal force because it is not in contact with anything other than the rope or the cord. That cord will exert a tension or a pulling force on M2. Let's call this T2. These are all the forces on the blocks, right? Now we have established that since the cord is massless and the pulley is massless as well as frictionless, that would mean the cord on both sides of the pulley will have the same tension. So T1 is equal to the magnitude of T1 is equal to the magnitude of T2 is the same. The cord will exert the same tension on both sides of the pulley. Let's write down Newton's second laws now. For this M1 in the x direction, we have plus x and plus y as chosen, and x summation of fx is equal to max. Summation of fx, only x force is T1 in the positive x direction, so positive T1 equals the mass of M1, which is 0.2 times ax. Ax is just A. Let's call this equation 1. What are the forces in the y direction? Again, if you look at M1, it is only moving in this horizontal direction, so no acceleration in the vertical direction. Therefore, we can say, using Newton's second law, f of y equals 0 because A is 0. That means the forces in the y direction are balanced with each other. So N1 is nothing but 0.2 times G. That is the normal force exerted on M1 by the surface, equal to its weight because there is no motion in the y direction. Now let's worry about the x equation for M2. Fx is equal to M2ax, and there is no x direction, so this won't work. It is only moving vertically because the mass is hanging freely, so there is no x direction. In the y direction, what do we have? We have this kind of system, and the system moves in this manner, right? The system moves downward. So we choose the axis so that acceleration is positive. That makes our lives easier. That makes writing Newton's second law without mistakes a lot easier, because signs can be an issue. So let's say plus y for this particular m2 is downward. So notice that we can choose different coordinate systems for different objects oriented differently. So m1 is oriented to move horizontally, so we choose this axis because in the direction of acceleration we have one positive axis. Because m2 is only moving vertically, we are free to choose another set of coordinate axes where we denote plus y to go downstairs or to go downwards, with the direction of acceleration being positive. All right, so summation of Fy is equal to MAY. Hence, then we can write down what are the forces. In the plus y direction, that is downwards now, it is 0.04 times G. Upward we have a tension force minus T2 is equal to M times AY. What is M? M is M2, which is 0.04, and AY is nothing but A2, right? But A2, let's call this A1, let's call this A2. So this is our equation 3. Now let's simplify all these equations and get to the tension in the cord. We have already established that the magnitudes of T1 and T2 are the same. So wherever you see T1 or T2, just replace those with T. So let's say that these are actually both T's. Since the masses are connected together via a massless cord and the pulley is frictionless, that also implies, in addition to this, the accelerations of both the boxes are the same. The magnitude of acceleration are the same. So anywhere you see A1 and A2, replace those with A. The magnitudes of the acceleration of the boxes are the same. So we have simplified our lives. We want to find T. Then what do? We have two equations that has T in it, and that must be our target. So let's solve equation 1 for A. 1 implies that A is equal to T over 0.2, T over 0.2, right? Just divide both sides by 0.2, you get what A is. Let's call this equation 4. Then we use equation 4 in equation 3, another equation with T in it, and now this is our target. This becomes 0.04 G minus T equals 0.04 A. Wherever you see A, replace A by equation 4, this expression, T over 0.2. Then bring all the T's to one side. So we have 0.04 G equals, add T to both sides so that this side T vanishes. On this side we have T plus 0.04 T over 0.2. Then if you solve for T, you can factor T out. We have 1 plus 0.04 over 0.2. Whatever this comes out to be, divide both sides by this number. So 0.04 times G is 9.8, divided by this number, 1 plus 0.04 over 0.2 equals T. So this comes out to be 0.33 newtons. This is the tension in the rope. The second part of the question asks me what is the acceleration of the block system. Remembering that we got T equals 0.33 newtons. This is the tension in the cord connecting the system. Alright, now our job is to find acceleration. It's time for us to use from the previous part, Newton's second law equations. So it's just a matter of algebra to know that since T equals 0.033 newtons and we have found the Newton second law equations for m1 equals 0.2 kilograms as this, then we can just put in 0.33 for t and solve for a. That will give us the acceleration of the system. We don't need to do the same thing for block m2 because, as we know by now, that acceleration is the same in this kind of system where the pulley is massless and frictionless along with the cord. Therefore, we have 0.33 equals 0.2a. Divide both sides by 0.2. This gives me the value for acceleration as 1.65 meters per second squared. This is the acceleration of the block system. Now let's get to the part of the question where we are asked to combine kinematics and dynamics to solve our problem. So what is it? How long does it take for the system to move 0.8 meters if the system is released from rest? So we know that how long refers to time, and time is a kinematic variable. We have so far used dynamics, that is Newton's second law, to find the force, the tension in the rope, the acceleration from Newton's second law, and then we are asked to find the kinematic variable time. Okay, what are we given? We are given that this is the system, the block system m1 and m2 is first held at rest. Initially both their velocities are 0, and then they're released from rest, and then they are accelerated as shown in the figure. Then let's note down what are the kinematic variables we know and find the target kinematic variable, which is the time. For m1 we have kinematic variable is delta x is 0.8 meters. This is the distance moved by the system. We want to find the time that the system takes to move this distance or displacement. We know the acceleration, which is 1.65 meters per second squared, and we know that initially the system was at rest. The same is true for m2 because they move together. So if m1 moves a distance of 0.8 meters, then m2 moves the same distance but in the vertical direction. So 0.8 meters. We don't know the time. The acceleration of the full system was 1.65 meters per second squared, and initially it was at rest. Okay, then we can use either of these equations to solve our problem for the target variable. Let's use m2. It doesn't matter which we use. So we use the equation delta y is equal to vi times delta t plus 1/2 ay times delta t squared. Delta y is 0.8 meters. This is equals to, let's forget about units. Initially this was at rest, so initial velocity is 0, plus 1/2 ay is 1.65, the acceleration of the system, times t squared. So 0.8 times 2 over 1.65 is what we get when we solve for t squared, and then to find t we just take the square root of this. Now when we take the square root, we know that we have two solutions, plus and minus. 0.8 times 2 over 1.65. However, know that time is never negative, time is always positive. So when you're solving for time, forget about the minus in the square root, and then therefore we get 0.97 seconds. This is the time the system requires to move 0.8 meters.